If you have some data that is stored in a relation between two different classes of variables, there might be some topological and geometric structure that you can use. This is joint work with a number of people at BAE Systems, as well as a student of mine, and was done in support of the DARPA SafeDocs project. If you're interested, there are a few papers you can read. And the motivation is to understand consensus file formats. Many different common file formats are defined by a consensus rather than a formal machine-parsable specification. Some of these had formal specifications, some of them didn't, but they've grown beyond that. So for instance, PDF or HTML and JavaScript are examples of file formats that are defined by consensus, as in there's a collection of different programs that can read them and write them. And they might contain some problems, especially problems that might show up when there are differences of opinion about what the files are supposed to mean. Now, how can you detect when a file is potentially bad? Because you can't exactly say, well, it fails the specification because the specification may not be so accurate. Well, this involves looking a little bit historically. So for instance, this talk focuses on PDF, and there have been, over the years, many different PDF standards of sorts. All of them have been written in plain technical English, and the slide here shows many different of them over the years. They're all similar. Many of them are mutually intelligible, but not all. It's a consensus, though. The standard is written in plain English. It's owned by the PDF Association. Used to be an Adobe standard, but that is spun off as an independent organization. Many different parsers or programs will read this PDF standard, but they sometimes make different choices when the file format is ambiguous. And of course, parsers being computer programs, they have bugs. So when files are not really compliant with the standard, the parsers will try to fix the files so that they can continue. This is not a good idea. It's not a good idea because it leads to differences in parser behavior, and these can lead to various kinds of exploits and malware. So how can you safely test some potentially dangerous files? Well, the best way to do this is to isolate the file and the parser so that it cannot do things it shouldn't do, even though it might try. So confine it to an environment, say a virtual environment or virtual machine, that has very limited input-output access. On the other hand, though, you don't get very much information out. You end up with what you might represent as a binary relation between files and parsers. That binary relation records which files were accepted by which parsers. So you might put a 1 if in a column representing a file. In a row representing a parser, you put a 1 there if that file was indeed successfully parsed, and a 0 otherwise. As we'll go on, you might expand the parsers to be specific other filters or messages that are produced by these files as they're read. And it probably is the case that you'll have lots more files than you do parsers. It doesn't really matter for the mathematics I'm going to show you. But the hypothesis is that anomalous files, potentially malicious files, or buggy parsers, or parsers that read different dialects, will be manifest somehow within the context of this relation, provided you have enough diversity of both files and parsers. In this talk, I'm going to focus mostly on a specially curated data set for the DARPA SafeDocs Evaluation 2 exercise. It consists of 10,000 PDF files, which were mostly sourced from Common Crawl, although some of them were not. They were modified by the test and evaluation team. Our team ran 22 different parsers against each file. So that's 22 parsers against 10,000 files, a lot of runs. And we captured the standard error output from these parsers, and then ran a battery of regular expressions against the output, the standard error output, to potentially identify whether or not a given parser accepted or rejected the file. Now, the files were actually ground truthed by the test and evaluation team as being valid or rejected according to the standard. They actually had someone on their team who works for the PDF Association who acted as a referee. And the files were given to us as two data sets, the internet-sourced data, which, as you might imagine, is majority Common Crawl, as well as the somewhat ominously named dangerous files. You can see there are a lot more internet-sourced files, 9,000 versus 1,000 dangerous files. The vast majority of the internet source files are valid, and about half of the dangerous files were rejected. Okay, so let's see what this data look like and how we can analyze it. If you draw up the data after we processed it with our 22 parsers, you get a matrix that looks a bit like what I'm showing on the screen. So these two images are matrices that have a total of 10,000 columns. So 9,000 columns in the plot on the left, the internet sourced files, because there are 9,000 files, and 1,000 dangerous files, i.e. 1,000 columns on the right. Now, the rows are certainly more than 22. I said we ran 22 parsers. We split up those parsers into a variety of regular expressions that ran on their standard error. And so we had just over 900 messages that we looked for from those parsers. How did we build those? It was kind of a manual process. But in any case, the messages, the rows, mean the same thing in the two data sets, whereas the columns, the files, do not. The files are in no particular order, and actually the messages are in no particular order as well, although they're somewhat blocked based on parser. That explains the horizontal streaking that you see, is that some parsers are just more noisy than others. So for instance, if you grab one particular file, that's a column, you can see where there are ones. I've marked those as black pixels. So this particular file produced a message from category-theoretic extract, category-theoretic stats, and a variety of others, and you can see what the regular expressions were that matched. So category-theoretic thought this file had some kind of type error. The different variants of category-theoretic, which are category-theoretic run with different runtime options, all found various kinds of type or syntax errors. And there are a variety of other parsers that produce some kind of error that we didn't successfully categorize, but we recognized was a problem. So some of these parsers produce a large amount of data, and we simply checked, did it like it or not? In the case of Hammer, that was a parser we have a very good control over. We understand how that one works. PDFium, on the other hand, is a parser that tends to produce very little useful output. And so we just know, hey, produce some kind of error, don't quite know what it is. So in any case, this particular file was deemed valid regardless of these errors. So even though that category-theoretic thought that there were some syntax errors or type errors, that was considered to be okay. This file happened to be unambiguously correctable according to the PDF specification. Category-theoretic is meant to be a PDF validator, and so it's a bit more grumpy than a typical parser. It's meant to be a little more stringent about following not only the letter of the law, but also the spirit. If we look instead of column-wise, row-wise, you can see that the rows correspond to different parsers, as I mentioned. And certain parsers are just noisier than others. They produce many of the same message for many files. This could well be an artifact of the parser. As I said, PDFium is rather uninformative. But it could also be an artifact of the regular expressions that we use to identify these messages. The regular expressions are handcrafted, and so therefore some of them are a little better than others. Okay, so the question is, are there any features in this data set? And before we look for geometry, let's ask, is there any topology? How would we do that? Well, you could imagine that I'm going to build some geometric information and from that extract some topological information. So for instance, each column being a point in space, each file being a point in space, we need some kind of distance measure. So for instance, I can compute the Hamming distance between files. That's easy enough. And if I do that, I can use that distance and render a multiple dimension scaling or a principal components analysis. So these are the two data sets rendered, showing you the first three principal components. The first three principal components are different for the two different data sets. That doesn't really matter too much, but you can see right away that the texture is rather different. The internet-sourced data is very clumpy. You can see some obvious clusters that are there, whereas the dangerous set is more spread out. I can really only see two visible clusters. What I've also done is I've colored the points, i.e. the files, as either black for valid files or gray for rejected files. You can see the internet-sourced files, the valid files cluster very tightly, whereas the dangerous files do not. What we're really interested in then is which files are misclassified. In a sense, the internet-sourced files are meant to be prototypical good files. The majority of them are valid. So any of the rejected are somehow misclassified in a sense. Versus the dangerous files, most of them are supposed to be bad. They're majority bad by a slight margin. And, well, if that's supposed to be prototypical dangerous files, then most of the valid files then are misclassifications. So the question is, can we identify these? So, as I said, the misclassified files seem to cluster fairly tightly. This suggests that specific tool chains or format peculiarities are being used and are giving rise to these behaviors. So this indicates the topology, i.e. the clustering structure, does matter. And if we can exploit it somehow, that will help us classify or fix the misclassifications of these files. So let's try to extract some topological features. Now, the classic topological feature for relational data like this is the Dowker complex. It's related to formal concept analysis. The way that you draw the Dowker complex is you say that each row is going to specify the vertex of, or specify vertices of an abstract simplicial complex, and each column is going to link together vertices specifying a simplex. So in this particular toy example, I have a binary relation. The letters are the vertices, the rows, and the columns specify some simplices. So for instance, you can see that the edge that I've highlighted in green from A to C corresponds to that second column. Its presence is witnessed by the fact that the second column has a 1 in the A and C rows and zeros everywhere else. Of course, you might have more than pairwise interactions. So the fourth column has a 1 in the C, D, and E rows. And the C, D, and E rows, having 1s there, means that you end up with more than an edge, you end up with a triangle. You might not get filled-in triangles because you may not see 3 ones in every three different ones in every row for a given set. So for instance here, A, B, and C, there are no columns that have 3 ones in them. So this is a difference between this situation here. This is filled in, this is not. The fact that there is no filled in loop here indicates the presence of some kind of format disagreement. The parsers A, B, and C don't all simultaneously accept the same file. There's always a bit of a disagreement. So this is an indication, at least intuitively, that topological features might be useful for studying file formats. Now, it's handy to think about binary relations category-theoretically, because this way we can build some analogies between the relations formally and the topological structure, the Dowker complex, as well as any additional geometric or statistical information we want to bring along. So let's formalize the category of relations. The category of relations has as objects triples, where the X and the Y sets are the rows and columns, so the parsers and the files, respectively. And the third element to the triple, the R, is a subset. So it's listing all of the file parser pairs that were accepted, or perhaps the file message pairs that occurred. As you might imagine, this generalizes neatly to entries with post-set values. And it's worth noting that the category of binary relations could also be thought of as the category of formal concepts as well. Now, the reason for calling this a category is because it has a notion of a morphism, or a structure-preserving map. I can map one relation to another, provided I map the rows and I map the columns, subject to some kind of compatibility condition. Anywhere where I had a 1 before, on the left in the domain, that maps to a 1 in the right in the codomain. So this green set of 1s that I've showed here in the row C, you see that maps to the third row, capital C. And those particular 1s get mapped to 1s in the other relation. And in particular, here's another collection of 1s that also maps to 1s. Again, this is preserving the formal concepts that are present. And for instance, here as well. So the Dowker complex is functorial, which means that if I transform my relation matrices, this in fact drags along the Dowker complex for the ride and induces a simplicial map. This is true for full generality. It's kind of an exercise to the reader to prove this. Now, unfortunately, the Dowker complex, although it is functorial, it is lossy. It is a forgetful functor. So here are 3 different relations that are all isomorphic, non-isomorphic in the category of relations. They're all different. Yet they all induce exactly the same complex up to isomorphism. So there's information being lost. Can we replace this information? Yes, we can. We can keep track of how many times a given column occurs and use that as a label on the simplex. So for instance, here the ACD simplex, which is a triangle, occurs 4 times in the relation. So we will label that simplex with a 4. A theorem, which is not actually altogether obvious. It's a bit of work to prove, but it's constructive, in fact. Algorithmically, it yields a way to transform a labeled simplicial complex into a relation. Not every labeled simplicial complex yields a relation, but up to isomorphism on relations, you get the same labeling. So that's pretty handy. And actually a much deeper theorem, which I'll outline by construction, is that this actually can be enriched to a covariant functor. So you get functoriality all the way, but not with the labeling. And part of the reason for that is there's actually 2 different ways you might do this labeling. You can keep track of the exact matches, as I just showed you. That yields what I'll call the differential weight. But you could also ask for how many times did that particular simplex ignore the other vertices? How many times did that occur? So for instance, the CD edge occurs 7 times in this relation, but exactly CD alone and not AB only occurs 3 times. So you get different numerical values. What's kind of neat is both of these are actually isomorphism invariants, and they can be determined from each other by various kinds of summarizations. How does this work? Well, as I said, it's an algorithmic and constructive proof wherein you iteratively remove labels and transmute them into columns. The column ordering is not determined by this, but that's within the same isomorphism class in the category of relations. Great. But the problem is that these weight functions are not functorial. So even though they're isomorphism invariants, they don't transform nicely if I transform relations. I can fix that, as I mentioned. In order to do that, it's helpful instead to render, instead of a simplicial complex, render it into a partial order. So let's draw the Hasse diagram for the phase partial order for that Dowker complex. The arrows indicate simplicial inclusions. You will note that these are subsets as well. So this is the same complex, but now drawn as a partial order. So at the bottom row are the vertices. At the top row are the maximum dimensional simplices. And in the middle are the guys in between. So in fact, they're stratified by dimension as well. The bottom row is vertices. The next row up are edges, and then triangles, and so on up. This does not have any tetrahedra, for instance. Okay, so our labeling just applies to these simplices, just as before. I'm going to label with total weights, counting how many times each of these occur, ignoring the other vertices in play. Turns out the differential weights are more useful in practice for some statistical reasons, which I'm not going to go into here. Okay, now if I look at the Hasse diagram of the phase partial order for all of the eval2 data, i.e. not a toy example, it's much larger. So as you go up, you get a higher dimension in the Dowker complex. That means more messages being occurred. So each one of these is a collection of messages. I've colored and sized the vertices based on how many files are present, i.e. that differential weight that I mentioned. Turns out most of the bad files appear near the top. I guess that's kind of reasonable because those are files that produce a lot of messages, whereas most of the good files end up kind of down near the bottom because the parsers tend to be quieter, report less to the standard error output. But you know, there's some cross-pollination here. But if you just sort of draw a line in the sand, you can get about 98% classification accuracy right out of the box. So that's pretty neat. Now, I made the point that you can enrich this to a representation, a functor. How do you do that? Well, it's actually pretty straightforward. Instead of counting the counts, actually keep track of the columns, i.e. the files. So which files exhibit which messages? This is why the total weight is reasonable, because now I'm saying which files exhibit which patterns of messages. And so, for instance, if you look at the column 3, the third file, that shows up in several different places on this diagram, because, for instance, that file 3 exhibits messages A, C, and D, so it appears at the top. And A, C, and D individually, of course, so it appears in 3 locations on the bottom, and of course in the middle as well. If we want the arrows to actually be functions on these files rather than inclusions on the sets, we need to reverse them so that they include. And as a result, you end up, interestingly enough, this diagram defines a co-sheaf, and this is a co-sheaf on the abstract simplicial complex, a co-sheaf of sets. In fact, actually, because of these are actually identifying formal concepts, you get complete simplices in each case. So you can think of this as a co-sheaf of simplicial complexes on a simplicial complex. This is not a general thing that always happens. Not every co-sheaf of sets is a co-sheaf of simplicial complexes in which each co-stalk is a complete simplex. But when they're formal concepts, then they are, and in fact that's what's happening here. So that's pretty cool. The topology is kind of interesting and indicates that the co-sections of this co-sheaf could be arbitrary complexes. So I've highlighted an open set in the Alexandrov topology for this simplicial complex. So start at the bottom and work your way up. If you do that, you get this shaded region. That's an open set. If you ask what the space of co-sections looks like, follow the co-gluing rules, you end up with, it's a co-sheaf of simplicial complexes, so you end up with a simplicial complex, the one I'm showing here. Well, that's kind of interesting. Here's another one. Just you can see that it's a different shape. They're not complete simplices, but they kind of fit together by way of gluing together the simplices that you see. Where? How do you glue them together? Well, you glue them together based on the labeling that's present. Well, that's pretty neat. And in fact, this Dowker complex, this Dowker co-sheaf, becomes functorial as well. Well, that's pretty neat. So the Dowker complex is functorial. As I said, for some mysterious reason, this appears to be a bit of a folk theorem, but it's not too hard to prove. And I would argue that if you're trying to prove this, the phase partial orders are much easier to work with than the simplicial maps. But in fact, why not just go for the whole thing? This Dowker co-sheaf, in fact, is a functor as well. Now, in order for this to work, you need to make sure that your category of co-sheafs is enriched to have enough morphisms. Without enough morphisms, this does not work. You need to be able to change the base space as well as the fibers. Most authors don't let you vary the base space in sheaf or co-sheaf morphisms. I say beats me why, but the truth of the matter is it's because most of the time people are studying sheaves or co-sheaves on a single space. Here you need to treat them on multiple spaces. Which multiple spaces? The Dowker complexes. So then, in fact, the proof that works for the Dowker complex just really basically lifts, I would say, without really any extra work. You just have to keep track of the vertices, which you're probably doing anyway, and so that's that. You're keep track of the vertices, you keep track of the files, you're basically doing that anyway, so it's not so hard. Now, why do we call it Dowker complexes? Well, it's basically because in 1952, Dowker wrote a paper that demonstrated that the homology of this complex, which we've been describing, is actually isomorphic to the homology of the complex you get if you transpose the matrix. So you switch rows for columns, and so in particular you switch out what the vertices are. The complexes can look rather different. Here's a Dowker complex and the Dowker complex for its transpose shown on the slide. They look rather different. They have totally different number of vertices. The maximum dimension of the simplices are different. The transpose one even has an extra flare, the 3 to 5 edge. But it turns out these are actually homotopy equivalent. So Dowker didn't prove that. He just proved their homology isomorphic, but in fact they're homotopy equivalent. And there are several other generalizations that are known. This comes down to some kind of duality result for lattices as well. Dowker's proof doesn't actually go through that. The proof that he wrote is a fairly elaborate subdivision argument. More recent papers do a much cleaner job of this. But here's an interesting observation. If you take a look at this co-sheaf that we've built, this co-sheaf of simplicial complexes on the Dowker complex, and you compute its space of global cosections, then in fact you get the Dowker complex of the transpose. When I saw this, this really got me thinking to say, I wonder if Dowker duality is really comes down to a global cosections computation. And in fact, if you could transform this Dowker cosheaf into a dual in some fashion, i.e. another cosheaf of simplicial complexes on simplicial complexes. Turns out that works. And not only does this work, because this Dowker cosheaf has the Dowker complex and its dual baked into it, the property is functorial. There's a duality functor. It's an endofunctor that acts on the category of cosheaves of abstract simplicial complexes on abstract simplicial complexes that exchanges the base space with the space of global cosections. The proof, as you might imagine, is going to be some kind of elaborate diagram construction. That's true. It works for all cosheaves of abstract simplicial complexes on abstract simplicial complexes. And it has the special property that when you're working with Dowker complexes, which, as I mentioned, are not every labeled abstract simplicial complex is a Dowker complex, and not every Dowker cosheaf, or rather, not every cosheaf is a Dowker cosheaf. When you focus on them, that this is an endofunctor on that subcategory as well. So that's all very special. How does this work? Well, let me just take an arbitrary cosheaf of abstract simplicial complexes on an abstract simplicial complex and show you how this works. So this is not the Dowker cosheaf representation for any relation. And you can see that because the cosections over C, the vertex on the bottom, is not a complete simplex. Okay, it's an empty triangle. So how does this work? Well, I'm showing here the base space and the global cosections. And now what I'm going to do is I'm going to compute what this duality functor is supposed to do. Of course, I haven't defined the duality functor for you, but basically what it does is it takes a look at every simplex, and it forms the union of all simplices whose costalks contain the simplex you're looking at. So if I want to compute, for instance, the dual cosheaf on the simplex 3, notice 3 is not in the base space here, it's the wrong type. It's in the base space of the dual. Well, what do I do? Well, what I find is I find all the places where 3 shows up in the costalks. There are 3 different locations here. I've marked them with blue circles. You take a look at their base simplices and take the union of them. When you do that, you get just the edge CD. For instance, if I wanted to find differently the costalk over 1, 3 for this dual cosheaf, again, I find all the places where 1, 3 shows up, happens to be the same. In this particular case, again, so still the edge CD. So if I run this calculation all over the diagram, I did this by hand, you end up with a different cosheaf. And in fact, what was previously the space of global cosections becomes the base space of this cosheaf. And what was the base space is now the global cosection space. So that's pretty cool. Now, the costalks might not be complete simplices, as I mentioned, if we're not dealing with Dowker cosheaves, i.e. images of this Dowker functor. But this duality functor preserves that subcategory. And that's the key idea in what makes the Dowker duality work. A pairing of this duality functor and the fact that the subcategory is preserved. As a result, you end up with a nice commutative diagram. With this nice commutative diagram, it says functoriality all around. So you have transposition on the left and duality on the right. And this cosheaf representation transforms a relation into a Dowker complex labeled up as this cosheaf representation. And so this is actually probably the most general form of Dowker duality that there is. And so really, as I said, given the definition of this duality functor that I just explained, the only thing you need to do is show that the image subcategory of the horizontal arrows is preserved. And there's a little bit of calculation to show that. Now, that was all very general. What does this imply for consensus file formats? Well, because of functoriality, any of these Dowker constructions are reasonable tools for studying parser behavior on files. In fact, they support all sorts of nice topological and geometric ways of looking at the files. If you will, the topology is all the Dowker complex. The geometry is then in its space of global cosections. Of course, because of duality, you are free to switch the interpretation if you like. In any case, the functoriality guides the process of summarization. If you're not really that interested in how many files occur, well, then you could start looking for good exemplars by looking for these topological loops, as I mentioned, or other clusters which are visible in the data, as I showed you a little earlier in this talk. And so, in essence, the statistics on the weight values makes some amount of sense because it is actually coming as a decategorification of this functor. In fact, that's very much true. You can do some statistics on these weights and get some very, very accurate classifiers come out. Now, functoriality also guides, by duality, the process of curating a file corpus. Corpora is the plural of corpus. So if I test the same set of parsers on two different corpora, how do you compare their results? Well, it tells you that you should be able to transform the one relation matrix into another and check to see whether or not you get ones in the right spot. And, well, if that's a lot of work, you can transform it into Dowker complexes and study it there. And in particular, you can study file parser relations or parser file relations, and you don't actually lose anything if you're careful. That's pretty neat because it means that if you want to classify files or want to classify parsers, you can do both. Now, this suggests that you should start thinking geometrically as well. So here's a different data set of PDF files. I have 6 different subsets of varying numbers of files. As in before, the rows of each of these 6 sets has the same meaning, but the columns are different. Again, there are various regular expressions. In this case here, I've got about 3,000 different messages being fired. There are 6 different sub-universes, 3 universes, and each universe is split good-bad. Just looking at it, it's pretty easy to discriminate good and bad based on the number of regular expressions that fire, how many messages you get. The bad files tend to be noisier than the good files in this case, but it's harder to tell the different universes apart. The textural differences are more subtle. So that suggests we ought to compare 2 different relations. Now, instead of being topological, we really need to think geometrically. The rows are the same for all of those 6 relations, but the columns are different. The files differ. So, in fact, we don't really care about shuffling rows and columns or permuting them or changing them in any other way. But we do want to know how far apart the relations are. So we need a distance metric for the objects of this relation that respect the isomorphism classes. So here are 2 relations. How might I compare them? Well, a natural thing to do is to start to match up columns. Count the differences that occur in each row. Essentially, what you're trying to do is find files which are different that have similar behaviors. All right, here's a potential matching. And that seems like, if I look at it, these matches yield a bunch of differences in the rows, as I've shown. So the first row has got two differences, the second's got 1, and so on. I've highlighted them in red. I can add a penalty for unmatched columns because that's definitely an unresolvable difference. Select the maximum row difference. Keep that sort of as an idea of how different they are, but then let's minimize over all the possible column matches. Of course, I want it to be a metric, so I need to symmetrize and take the maximum. This yields a metric on relations. As you might imagine, this has got lots of searches all over it. That's kind of unpleasant. But one thing that you can do, and this is a nice discovery of my student Ken Ewing, is that you can much, much faster estimate this, bound it, although not actually know for sure. It's not necessarily an exact value. As if you lexically pre-sort your relations, then you can bound the sizes of the matches that you're making without doing any calculation. And so you can end up with a bound on the distance very quickly. In fact, amazingly enough, this distance is a well-defined metric on the isomorphism classes of the category of relations I defined earlier. What that means is, of course, if you shuffle the columns, you don't change the isomorphism class, and in fact, you don't change the distance either. It is, in fact, a metric. Distance is 0 if and only if the 2 relations are isomorphic, so that's pretty cool. And the distance bounds the difference between the Dowker weight functions, both the total and differential weights. Now, as you might imagine, since the total and the differential weights are rather different, this is kind of a loose bound, and that's true. Well, okay, great. We can go ahead and use this algorithm to this lexical sort and then distance metric as an algorithm to compare these universes. So here are the 6 sub-universes, and I've highlighted them based on the bound. Now, you can pretty clearly see the good files. That's the first 3 rows and the last 3 columns. Those are the good files. Versus the bad files, you can see they're quite different. The good files are similar to the good files. That's pretty nice. The bad ones are kind of different from each other, and you would imagine that this ought to be symmetric and have 0 diagonal, but there's some sampling error. That's entirely possible. I've only grabbed 1,000 files from each subuniverse. There are a lot more. And as I mentioned, this is a bit of a loose bound. So that's pretty neat. So this means that this Dowker complex idea is both topological and geometric and even categorical. So that's pretty nice. So did I say anything that was specific to PDF? Actually, no. All of the file format specific stuff happens at the beginning when you're collecting the messages or features. So provided you can do that, you can work with other formats. In fact, I showed you PDF. We've also made this work on MPEG files, on CSV files, and JPEG files, without a whole heck of a lot of work. Now, what constitutes a feature can be a bit amorphous then. We've used parsers and messages, but you can use system call stats, as in how frequently does a file induce the computer to make certain system calls. You could use some machine learning results. You could look at traces or grammar productions. Lots of other things, kind of limited by your imagination. The point is, it doesn't actually matter what these are if you work with this geometric information, which is ultimately kind of statistical. And so the conclusion is these Dowker complexes are useful and interesting in their own right, and they're quite powerful as data analytic tools. I suggest you go play with these kind of things. They're easy enough to code up. I've got a bunch of references that you might enjoy, and certainly I'm happy to entertain questions and discussion. Thanks for watching.